Okay, let's get into it. Number 11. The Birthday Paradox. Picture a room with 23 people in it. Just 23. A small classroom, a decent dinner party, a bus that's mostly full. Now bet me that two of them share a birthday. Same day, same month. You'd probably take that bet, right? There are 365 days in a year, and only 23 people. Feels like a sucker's bet. It isn't. In fact, you'd lose. With 23 people, the odds that at least two share a birthday are already just over 50%. Add a few more, and it climbs fast. At 70 people, it's essentially certain, over 99.9%. Here's where our intuition trips. When you hear shared birthday, your brain quietly rewrites the question into, does someone here share my birthday? And that version really is a long shot. You'd need hundreds of people for even odds on that. But that's not the question. The question is whether any two people match. And that's a very different animal. Because it's not about people, it's about pairs. With 23 people, the number of possible pairings isn't 23. It's 253. Every one of those pairs is its own little lottery ticket, its own chance at a match. Line up 253 chances, and suddenly a coincidence isn't a coincidence anymore. It's the expected result. The math is almost rude about it. The chance that any single pair does not share a birthday is 364 out of 365. Very high. But multiply that near certainty by itself 253 times, once for every pair, and it decays to about 49.9%, which means the odds of at least one match tip just past half. The tiny cracks add up. This was worked out formally by the mathematician Richard von Mises back in 1939, and it has a name that fits: the veridical paradox. Something that feels flat out wrong and is nonetheless completely true. It's not a trick of language. It's arithmetic that refuses to match your gut. And it's not just party trivia. This exact effect, the way matches hide inside pairs, is how cryptographers break certain security systems. They call it a birthday attack. The same quiet math that ruins your bar bet can crack a digital signature. So next time you're in a room of 23 strangers, look around. The coincidence is already there. You just haven't found it yet. Number 10. The Potato Paradox. You buy 100 pounds of potatoes. The label, for reasons we won't question, tells you they're 99% water. 1% potato, 99% water. Fine. You leave them out in the sun, and a little water evaporates, until they're now 98% water. Just 1 percentage point drier. Quick, how much do they weigh now? Your gut says 99 pounds, maybe 98. You lost 1% of something, so shave a pound or two off the top. Reasonable. Also wrong. The answer is 50 pounds. Half. You lost half your potatoes to a single percentage point. Let me walk you off the ledge, because I know how that lands. The mistake is that you're staring at the water. Don't watch the water. Watch the part that isn't water, the dry potato matter. At the start, the potatoes are 1% dry stuff. 1% of 100 pounds is 1 pound. That 1 pound of actual potato is the only thing that never changes. Water leaves. Potato solids don't. Now here's the move. At the end, the potatoes are 98% water, which means they're 2% dry matter. But the dry matter is still that same 1 pound. It never went anywhere. So now, 1 pound has to represent 2% of the total. And if 1 pound is 2% of the whole must be 50 pounds. That's the only number that works. Read it again if you need to. Everyone does. The water went from 99% to 98%, a rounding error, a shrug. But the dry fraction quietly doubled, from 1% to 2%. And doubling the fraction means halving the total. A whisper on one side of the ledger, an earthquake on the other. This is another one of those veridical paradoxes, true no matter how much your brain squirms. There's no hidden catch, no sleight of hand. It's just that percentages are slippery, and we anchor on the big, showy number, the 99, instead of the tiny, stubborn one that's actually running the show. It shows up anywhere you track concentration instead of quantity. Drying fruit, mixing solutions, even certain financial ratios. Focus on the wrong number, and reality will mug you in broad daylight. So a single % of water walks out the door, and half your potatoes go with it. Same sack, same sun, completely different world. Number 9. The Coastline Paradox. Simple question. How long is the coastline of Britain? Feels like the kind of thing that has an answer sitting in an atlas somewhere. It doesn't. Not really. Because the honest answer is, it depends on the size of your ruler. And the smaller your ruler, the longer the coast gets, with no ceiling. This started with a man named Lewis Fry Richardson, sometime before 1951. He was studying whether the length of a border between two countries affected the odds they'd go to war. And he hit something strange. Portugal reported its border with Spain as 987 kilometers. Spain reported the same border as 1,214 kilometers. Same border. A difference of over 200 kilometers. Nobody was lying. They just used different measuring sticks. Here's why that happens. Measure Britain's coast with a 100-kilometer ruler, laying it end to end, and you get roughly 2,800 kilometers. Your big, clumsy ruler skips straight across every bay and cove. Now switch to a 50-kilometer ruler. It dips into inlets the big one ignored, and the total jumps to about 3,500 kilometers. Drop to a 1-kilometer ruler, tracing every little headland, and the coastline explodes past 8,000 kilometers. And it never stops. Every time you shrink the ruler, you find smaller wiggles to trace. Bays inside bays. Rocks beside rocks. Grains of sand beside grains of sand. Each level of detail adds length, and the total climbs toward infinity. A finite island. An unbounded edge. The mathematician Benoit Mandelbrot seized on this in a 1967 paper with a beautiful title, How Long is the Coast of Britain? He realized coastlines live in a strange in-between space. A straight line is one-dimensional. A filled square is two-dimensional. But a coastline is somewhere in the crack between them, roughly 1.25 dimensions for Britain's west coast. Later, he'd give these in-between shapes a name we all know now. Fractals. And that's the thing that should get under your skin. This isn't some abstract mathematical monster cooked up to break your brain. It's the shape of the ground you walk on. The edge of every continent, every lake, every island is a fractal with no fixed length, hiding infinity in plain sight. So, how long is the coast of Britain? However long you want it to be. Just tell me the size of your ruler, and I'll tell you your answer. There isn't a true one waiting underneath. Number 8. Simpson's Paradox. Here's a claim that sounds impossible. A medical treatment can work better for men, and better for women, and yet be worse for people overall. Better for every group, worse for everyone. Same numbers. Both true at the same time. Welcome to Simpson's Paradox, the place where statistics turns on you. The most famous real example comes from the University of California, Berkeley in 1973. The graduate school looked at its admissions and saw something alarming. About 44% of male applicants were getting in, versus about 35% of women. That's a big gap. It looked like open discrimination, and it turned into a lawsuit. But then researchers did something simple. Instead of lumping every applicant into one giant pile, they looked department by department, and the bias vanished. Not a single department was significantly favoring men. In fact, when you broke it down properly, there was a slight tilt in favor of women. The overall numbers screamed one thing. Every individual piece said the opposite. So what happened? It wasn't the admissions officers. It was where people applied. Women were applying in larger numbers to the most competitive departments, the ones with brutal rejection rates for everybody. Men were applying more to departments that admitted most of their applicants. Each department was fair. But because women were funneling into the hardest doors, their overall acceptance rate came out lower. The pattern in the whole was the exact reverse of the pattern in every part. This is the trap. When you combine groups that are different in some hidden way, a lurking variable, the combined number can flip the direction of the truth. And here's what makes it genuinely unsettling. Both views are mathematically correct. The aggregate isn't a lie. The breakdown isn't a lie. They just answer different questions, and they disagree. Now think about how often we get handed one number and asked to trust it. Which drug works better? Which school performs better? Which policy helps? Simpson's paradox is proof that a single headline statistic can point you confidently in exactly the wrong direction and never once break the rules of math. The lesson isn't that numbers lie. It's scarier than that. Numbers can be completely honest and still mislead you, depending only on whether someone chose to split the data or stack it. The story lives in how you slice it. So the next time a chart makes something obvious, ask the quiet question, what happens if we break this apart? Sometimes the truth flips the moment you look closer. Number 7. The St. Petersburg Paradox. Let me offer you a game. I flip a fair coin. If it comes up heads on the first flip, I pay you $2, and we're done. Tails, I flip again. Heads on the second flip pays $4. Heads on the third pays $8. Every flip it survives, the prize doubles. 16, 32, 64, on and on, until heads finally lands. Now the real question, how much would you pay me, up front, to play this game once? $10? $20? Hold that number. Because here's what the mathematics says. The fair price to enter this game is infinite. You should be willing to hand over every dollar you will ever earn for one round. Here's why. To find what a gamble is worth, you weigh each prize by its chance. 50% chance of $2. That's worth $1. Then there's a 1 in 4 chance of winning $4. Another $1 of value. A 1 in 8 chance of $8. One more dollar. Every single possible outcome contributes exactly $1 of expected value. And there are infinitely many outcomes. 1 plus 1 plus 1 forever. The expected payout doesn't settle on a number. It runs off to infinity. And yet, nobody, and I mean nobody, would pay $1,000 to play this. You wouldn't. I wouldn't. Some cold-eyed logician who trusts the math completely still wouldn't. Because deep down, we know the truth. You'll almost certainly win $2 or $4 and walk away. The monster payouts are real, but so rare they might as well be ghosts. This puzzle is nearly 300 years old. It was posed by Nicholas Bernoulli in 1713 and analyzed by his cousin Daniel Bernoulli in 1738 in a paper he published in the city of St. Petersburg, which is where it got its name. And Daniel's answer changed how we think about risk forever. He said, expected value is the wrong measuring tool because money isn't worth the same to everyone. Your first $1,000 can change your life. Your 10 millionth barely registers. He called this idea utility, the real felt value of money, and it flattens the infinite prize back down into something a human would actually pay a few dollars for. So the St. Petersburg Paradox is the moment cold arithmetic and human judgment split apart. The math says infinity. Your gut says maybe $10. And the strange, humbling truth is, your gut was right. It took the birth of an entire science to prove it. Number 6. Parrondo's Paradox. 2 games, Game A and Game B. I've rigged them both. If you sit down and play Game A over and over, you slowly lose all your money. Play Game B over and over, same story, you go broke. 2 losing games. Guaranteed losers, both of them. Now here's the impossible part. If you switch back and forth between these 2 losing games, you win. Reliably. Consistently. Losing plus losing equals winning. Read that again because it sounds like nonsense, like saying 2 holes make a hill. This is Parrondo's Paradox, discovered in 1996 by a Spanish physicist named Juan Parrondo, and it is 100% real. Not a rounding trick, not a scam. Real, rigorous mathematics. So how can it possibly work? The secret is that the 2 games aren't strangers. They're linked. Game A is simple, a slightly unfair coin that bleeds you slowly. But Game B is sneaky. Game B changes its own rules depending on how much money you currently have. When your cash is in one state, B gives you gentle odds. When it's in another state, B punishes you hard. Left alone, Game B traps you in the bad state most of the time, and you lose. But now, bring in Game A. Game A doesn't win anything on its own, remember. What it does is stir the pot. It keeps nudging your total up and down, shuffling which state you're in. And that shuffling keeps knocking you out of Game B's punishing trap and into its generous one. Game A is the losing game that keeps setting up the wins for Game B. Alone, each one sinks. Together, they row. The reason this feels so wrong is that we assume combining is the same as averaging. 2 bad things should average out to a bad thing, but that rule only holds when the things are independent. The moment they influence each other, all bets, quite literally, are off. The whole becomes something neither part could ever be. And this isn't just a gambling curiosity. Physicists find the same pattern in what they call ratchets, systems that turn random jostling into directed motion. It shows up in finance, in engineering, and biologists have used it to explain how certain organisms survive by flickering between 2 losing strategies. Some researchers even reach for it in cancer treatment, alternating therapies that each fail on their own. 2 dead-end roads. Take them in the right rhythm, and they carry you somewhere neither one could reach. Sometimes the way to win is to lose, on purpose, in just the right order. Number 5. The Braess Paradox. You're a city planner. Traffic is terrible. So you do the obvious thing. You build a new road. A shiny shortcut, right through the worst of the congestion. More roads, more capacity, less traffic. That's just common sense. Except sometimes you flip the switch, open the new road, and the traffic gets worse. Everyone's commute gets longer. You added a road and slowed the entire city down. This is Braess's Paradox, named for the German mathematician Dietrich Braess, who described it in 1968. And the maddening part is that nobody is behaving badly. Every single driver is doing exactly what you do, picking the route that's fastest for them, right now. The disaster is what all those individually smart choices add up to. Here's the shape of it. Imagine 2 routes to work, and each one has a stretch that gets slower the more cars pile onto it. Normally traffic splits between them, and it balances out. Then you build a fast connector that lets drivers hop from one route to the other. Suddenly, everybody sees the same tempting shortcut, and everybody piles onto the same crowded stretches to reach it. The connector that was supposed to help becomes a funnel, jamming the very roads it feeds. Each driver's clever move makes the whole worse, including for themselves. And here's the punchline that makes it more than a theory. It works in reverse, in real cities. In Stuttgart, planners added roads and the traffic didn't improve, until they closed a stretch of newly built road, and then it did. In Seoul, South Korea, they tore out an entire 6-lane highway, the Cheongye Expressway, expecting chaos, and traffic around the city actually sped up. In New York, closing a section of 42nd Street for Earth Day in 1990 eased the congestion instead of causing gridlock. Remove a road, and everyone gets home faster. What makes this genuinely unsettling is that it breaks a rule we all believe in. More options should never make things worse. Give people another choice, and, worst case, they ignore it. But in a network of self-interested players, a new choice can drag everyone into a worse equilibrium that no one wanted, and no one can escape alone. It's a quiet lesson that reaches way past traffic, into power grids, the internet, even how teams organize. Sometimes the fix isn't adding, it's subtracting. Sometimes the kindest thing you can do for a crowd is take an option away. Number 4. The Mpemba Effect. Take 2 cups of water, one hot, one cold. Put them both in the freezer. Which one turns to ice first? Obviously the cold one. It's got a head start. It's already closer to freezing. This is barely a question. And yet, under the right conditions, the hot water can freeze first. The one that started further from ice gets there sooner. And here's the truly wild part. After thousands of years, we still can't fully explain why, or even fully agree that it's real. This is the Mpemba Effect, and its history is a story in itself. Aristotle wrote about hot water freezing quickly back in the 4th century before Christ. Francis Bacon mentioned it. René Descartes mentioned it. Then it just faded from science for centuries. Until 1963, when a Tanzanian schoolboy named Erasto Mpemba was making ice cream in a cooking class. He was in a hurry, so he shoved his hot mix into the freezer without cooling it first, and it froze before his classmates' cooled mixtures. His teacher basically told him he was confused, but Mpemba wouldn't let it go, and eventually he teamed up with a physicist named Dennis Osborne, and together they published a paper in 1969 that put the effect on the map and gave it the boy's name. A kid making dessert, arguing with the whole weight of physics, and forcing it to look again. So, why would hot water win? Scientists have thrown out a whole shelf of explanations. Maybe the hot water evaporates a little, so there's less of it left to freeze. Maybe convection currents move the heat around faster. Maybe dissolved gases escape from the hot water and change how it behaves. Maybe it's something subtle in the hydrogen bonds between the molecules. Every explanation works sometimes and fails other times. And then, in 2016, a careful study went looking for the effect under tightly controlled conditions and couldn't reliably find it at all, which threw the whole thing into doubt. Was Mpemba's ice cream a fluke? Some physicists now argue the effect isn't robust, that it depends entirely on how you define the moment water counts as frozen. Others insist it's real under specific setups. The argument is still going. Think about that. Not a black hole. Not the edge of the universe. Water. In a freezer. The most ordinary substance on Earth, doing something we've watched for 2,400 years. And we still can't close the case. The deepest mysteries aren't always far away. Sometimes one is sitting in your kitchen. Number 3. The Bell Spaceship Paradox. 2 identical spaceships sit in deep space, one behind the other, and between them runs a thin, delicate thread, pulled just taut. At the exact same instant, both ships fire their engines. Same acceleration, same direction, perfectly in sync. They speed up together, keeping the same distance apart the whole time, at least as you see it, watching from the ground. Question: does the thread break? Your gut says no. Of course not. They're moving in perfect lockstep. The gap between them never changes, so the thread just goes along for the ride. That's the obvious answer. It's also wrong. The thread snaps. And the reason it snaps is one of the strangest truths in all of physics. This puzzle was first laid out by 2 physicists, Dewan and Barron, in 1959, and later sharpened by the famous physicist John Stuart Bell in 1976. And Bell did something wonderful with it. He took it around to the professional physicists at CERN, one of the great laboratories on Earth, and they argued. Many of them got it wrong at first. If the experts stumble, you're in good company. Here's the resolution, and it's a doozy. Einstein's relativity tells us that a moving object contracts along its direction of motion, not an illusion, a real physical shortening. Now, a solid ruler flying through space wants to shrink to a shorter length, but in our setup, the two ships are forced to stay the same distance apart because they accelerate identically as measured from the ground. The gap is not allowed to contract, and that's the trap. Space between the ships wants to compress. Relativity demands it, but the synchronized engines refuse to let the ships drift closer together. So the thread is caught in a tug of war between what relativity wants and what the ships are doing. Stretched between those two, it builds up stress. And as the ships go faster and faster, that stress climbs until the thread reaches its limit and tears itself apart. Nothing pulled on it. No hand yanked the ends. Space itself did it. Sit with that, because it rewrites something you thought you understood. We picture space as an empty stage, a nothing, just the backdrop where events happen. This paradox says, no, space has structure. It can stretch. It can hold tension. It can reach into a thread and snap it, using nothing but geometry. The emptiness between the stars isn't nothing. It's a fabric. And under the right conditions, that fabric pulls tight. Number 2. The Quantum Cheshire Cat. In Alice in Wonderland, there's a cat that fades away until only its grin is left, hanging in the air with no cat underneath it. Alice says she's often seen a cat without a grin, but never a grin without a cat. It's the most absurd thing in the book. Now here's the part that should keep you up tonight. In quantum physics, we have actually done it. We've separated a particle from one of its own properties. The cat goes one way. The grin goes another. Let me be careful, because this is real, and it's stranger than the fiction. The idea came from the physicist Yakir Aharonov and his collaborators around the year 2001. And then, in 2014, a team ran the actual experiment, published in the journal Nature Communications. They took neutrons, tiny particles from inside the atom, and sent them through a device that splits their possible paths in two. A neutron carries a property called its magnetic moment, basically a little internal compass needle, its spin. You'd think, wherever the neutron goes, its magnetic moment goes too. They're the same object. You cannot have the needle without the particle. Except the experiment found something else. The measurements showed the neutron traveling down one path, while its magnetic moment, its spin, appeared to travel down the other. The particle on the left, its property on the right, a cat, and its grin walking separate roads. Now, how do you even measure something without wrecking it? Because normally, looking at a quantum system slams it into a single, definite state. The trick is what physicists call weak measurement. Instead of one hard look that collapses everything, you take a huge number of impossibly gentle peaks, each one barely touching the system, and let the faint pattern build up. And the pattern that emerged was a particle and its property in two different places. I'll be honest with you, because good science demands it. This is fiercely debated. Some physicists argue the whole thing is just ordinary quantum interference, wearing a spooky costume, that nothing literally, physically detaches from the neutron. The measurements are solid. What they mean is where the fight is, but even the modest version is staggering. At the quantum scale, the tidy idea that an object and its qualities are welded together, that a thing is always where its properties are, stops being obviously true. Location and property come unstitched. Lewis Carroll wrote it as the height of nonsense, a grin with no cat. Nature read it and quietly said, "Hold on, watch this." Number 1. Newcomb's Paradox. Two boxes sit on a table in front of you. Box 1 is transparent, and inside it you can see $1,000. Right there, yours for the taking. Box 2 is sealed shut, and it holds either $1 million or absolutely nothing. You have a choice. Take only the sealed box, or take both boxes. That's it. Simple. And it may be the most argued over decision in modern philosophy. Here's the catch that breaks everything. Before you walked in, a predictor, a being that is almost never wrong, looked at you and forecast what you would choose. And the predictor already filled the boxes based on that forecast. If it predicted you'd greedily grab both boxes, it left the sealed box empty. If it predicted you'd humbly take only the sealed box, it put the full million inside. The boxes are already filled. The money is already there, or already not. Nothing you do now can change what's inside. The puzzle was created by a physicist named William Newcomb and made famous by the philosopher Robert Nozick in 1969. And what makes it immortal is that two flawless lines of reasoning give you opposite answers, and both feel completely airtight. Argument 1. The predictor is almost never wrong. Everyone who took both boxes walked away with a measly 1,000 because the predictor saw them coming and left the big box empty. Everyone who took just the one box walked out a millionaire. So take the one box, obviously. Follow the track record. Argument 2. Wait, the boxes are already filled. That's done. It's in the past. Sealed. If the million is already in there, taking both boxes gets you the million plus 1,000. If it's already empty, taking both at least gets you the 1,000. Either way, taking both boxes wins you an extra $1,000, no matter what's inside. So take both, obviously. It's just free money. Both arguments are valid. Both are ironclad. And people don't drift toward one side. They split almost exactly in half, each convinced the other side is being ridiculous. Nozick himself noticed this strange, even division. And underneath the boxes, there's a deeper thing staring back at you. If a predictor can know your choice before you make it, well enough to bet $1 million on it, then in what sense is the choice yours? Were you ever really deciding, or just discovering, what you were always going to do? The boxes aren't really about money. They're about whether the future is open or already written, waiting for you to catch up to it. You reach for a box, but maybe the reaching was set long ago. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.